Students, my name is Amit Khan. In this video, we will discuss about the topic operational amplifier. The name of the subject is Fundamentals of Electronics. It is for mechanical third semester. So at first we will know about what is operational amplifier, that is op-amp. An op-amp is an integrated circuit that can amplify weak signals. It has two input pins and one output pin. Its basic role is to amplify and output the voltage difference between the two input pins. It is a monolithic integrated circuit. It is a special type of direct coupled high gain amplifier with very large input impedance and a very low output impedance. The unique feature of op-amp makes it suitable for performing a variety of linear and nonlinear applications. A negative voltage shunt feedback is normally employed to control the op-amp. Next we can see the symbol and block diagram of op-amp. This is there is the symbol of the op-amp. V1 is the inverting input and V2 is the non-inverting input. Then comes the block diagram. You can see that the input first goes to the differential amplifier and then goes to the gain stage, then the level shifter, and then to the emitter follower. From the emitter follower we get the output. This is the IC representation of op-amp. It is 741 op-amp. Here the number 1 and number 5 pin is offset null. Number 2 is inverting input. Number 3 is non-inverting input. Then comes the ideal characteristics of op-amp. It is a negative feedback is applied in op-amp. The output resistance is 0. Open loop gain is infinite and it has infinite bandwidth. And common mode rejection ratio, that is CMRR, is also infinite. Then comes the different applications of op-amp. The first one is inverting amplifier. It is also known as inverting operational amplifier or inverting op-amp. It is a circuit which produces an output which is out of phase with respect to its input by 180 degree. The circuit diagram of inverting amplifier is given. The gain is minus RF by R1, where Vi minus V1 is I1 into R1, II into Ri, and V1 minus V0 is IF into RF. However, we know that an ideal op-amp has infinite input impedance, due to which the currents flowing into its input terminals are 0. So I equals to 0, thus we can see that Vi minus V1 equals to IF into Ri, and V1 minus V0 is IF into RF. Then we can see that as we have grounded the non-inverting terminal, so 0 voltage appears at the non-inverting terminal. So V2 is 0 and V1 is also 0. So 0 minus V0 is IF into RF. So from this equation we can write that V0 by Vi, or V output by V input, equals to minus RF by Ri. It is the voltage gain. So this indicates that the voltage gain of the inverting amplifier is decided by the ratio of the feedback resistor to the input resistor, with the minus sign indicating the phase reversal. This type of inverting amplifiers exhibit excellent linear characteristics which make them ideal as DC amplifiers. Then comes the non-inverting amplifier. Here the op-amp has two input terminal pins. One is inverting and the other one is non-inverting. The inverting pin denoted by the minus sign, and the non-inverting pin is denoted by the positive sign. So the circuit diagram is given. Here in the circuit we connect an external resistance R1 and feedback resistance Rf. So we can write V1 by R1, that is equals to V0, that is V output minus V1 by Rf, by applying Kirchhoff's law, Kirchhoff's current law. So now if we assume that the input voltage applied to the non-alternating terminal is Vi, so we can get that V1 equals to Vi for an ideal op amp. So we can write that Vi divided by R1, that is equals to V output minus V input divided by Rf. From this equation we can derive that V output by V input equals to 1 plus Rf by R1. This is the closed loop gain for the circuit. From the expression of voltage gain of an non-inverting op amp, it is clear that the gain will be unity when Rf equals to 0 or Rf tends to infinite. Then comes op amp as a summing amplifier. Here we can see the circuit diagram. It becomes, in this summing diagram amplifier circuit, the output voltage V out becomes proportional to the sum of the input voltage V1, V2, V3, etc. So IF equals to I1 plus I2 plus I3, that is equals to minus V by R. I equals to V by R, that is minus V1 by R in plus V2 by R in plus V3 by R in, and so on. So the inverting equation is V out equals to minus Rf by R in into V in. Then minus V out equals to Rf by R in into V1 plus Rf by R in into V2 plus Rf by R in into V3. Then comes what is virtual ground of an op amp. A mechanical ground in a circuit is the ground for both voltage and current. The voltage of the point which is directly connected to the ground is 0, and an infinite current can flow through the ground. In op amps, the term virtual ground means that the voltage at the particular node is almost equal to ground voltage, that is 0 volt. It is not physically connected to ground. So this concept is very useful in analysis of op amp circuits, and it will make a lot of calculations very simple. The diagram of virtual ground is shown in the figure. Then comes slew rate. The slew rate is defined as the maximum rate of change of an op amp's output voltage and is given units of volts per microsecond. Then comes differential amplifier. The differential amplifiers amplify the difference between the two voltages, making this type of operational amplifier circuit a subtractor, unlike a summing amplifier, which adds or sums together the input voltage. So the circuit diagram of differential amplifier is given here. Here I1 equals to V1 minus VA by R1, then I2 equals to V2 minus VB by R2, and IF equals to VA minus V out by R3. And the summing point is VA equals to VB and VB equals to V2 into R4 divided by R2 plus R4. Then if V2 equals to 0, then V out equals to minus V1 into R3 by R1, and we can get that V out is equals to minus V1 into R3 by R1 plus V2 into R4 by R2 plus R4 into R1 plus R3 by R1. So the differential amplifier equation is V out equals to R3 by R1 into V2 minus V1. Then comes CMRR. What is CMRR? CMRR is common mode rejection ratio. It is the ratio of the common mode gain to the differential mode gain. Then comes the differentiator circuit. Op amp as differentiator. The circuit diagram is shown in the figure. If the capacitor blocks any DC content, so there is no current flow to the amplifier summing point, resulting in zero output voltage. That is the virtual ground. Point X. The capacitor only allows the AC type of input voltage to pass through the whose frequencies depend on the rate of change of the input signal. At higher frequencies, the reactance of the capacitor is much lower, resulting in a higher gain and higher output voltage from the differentiator amplifier. However, at high frequencies of an op-amp, differentiator circuit becomes unstable and will start to oscillate. So, to avoid this, the high frequency gain of the circuit needs to be reduced by adding an additional small value capacitor across the feedback resistor RF. So the current flowing through the capacitor is IF, that is equals to minus V out by RF, and the voltage across the capacitor Q equals to C into V in, that is the charge on the capacitor is Q equals to C into V in. So the rate of change of the charge is dq dt, that is equals to C into dV in by dt. But dq dt is the capacitor current. So from here we can get that minus V out by RF, that is equals to C into dV in dt. So the output of the op-amp differentiator is V out equals to minus RF into C into dV in by dt. Then comes op-amp as integrator. The circuit of integrator is given here. As the name implies, the op-amp integrator is an operation amplifier that performs mathematical operation of integration. That is, we can cause the output to respond to changes in the input voltage over time, as the op-amp integrator produces an output voltage which is proportional to the integral of the input voltage. We know that the voltage on the plates of the capacitor is equal to the charge on the capacitor divided by its capacitance, giving Q by C. Then the voltage across the capacitor is output voltage V out, that is equals to minus V out equals to Q by C. So Vc equals to Q by C. That again we know Vc equals to Vx minus V out, that is 0 minus V out. So minus dV out by dt, that is equals to dq by dt into 1 by C. But dq dt is electric current, and so the node voltage of the integrating op-amp at its inverting input terminal is 0. So I in is equals to V in minus 0 by R in, that is V in by R in. The current flowing through the feedback capacitor is given IF equals to C into dV out by dt, that is equals to C into dq by dt into 1 by C, that is dV out into C by dt. Then assuming that the input impedance of the op-amp is infinite, so no current flows into the op-amp terminal. Therefore, the nodal equation at the inverting input terminal is given as I in equals to IF, that is equals to V in by R in, that is dV out into C by dt. So the output of the op-amp as integrator becomes V out equals to minus 1 by R in into C integral 0 to dV in dt. Then comes op-amp as a buffer. It is also called as voltage follower circuit. The circuit diagram is given here. If the voltage is transferred unchanged, the amplifier is a unity gain buffer. Here V in equals to V out minus Vd, that is equals to V out into 1 minus Vd by V out. Vd by Vd divided by V out is 10 to the power 6 for open loop gain. So V out becomes approximately equal to V in. So the output voltage here is almost equal to the input voltage. Then comes the comparator. This is the circuit diagram of comparator. Op-amp as comparator is given. V in, when input voltage V in is greater than V reference, that means reference voltage, then V out equals to plus VCC, and when V in, that is input voltage, is less than V reference, that is reference voltage, then output voltage equals to minus VCC. So when we increase the input voltage V in so that its value is greater than the reference voltage on the inverting input, the output voltage rapidly switches high towards the positive supply voltage plus VCC, resulting in a positive saturation of the output. And if we reduce again the input voltage, so that is slightly less than the reference voltage, the op-amp output switches back to its negative saturation voltage, acting as threshold detector. Then comes Smith trigger. This circuit is also called as regenerative comparator circuit. The circuit has a positive feedback and hence will have a regenerative action which will make the output switch levels. Also, the use of positive voltage feedback instead of negative feedback aids the feedback voltage to the input voltage instead of opposing it. So the use of this circuit is to remove the difficulties in a zero crossing detector circuit due to low frequency signals and input noise voltages. The circuit diagram is given in the figure. The purpose of this circuit is to convert any regular or irregular shaped input waveform into a square wave output voltage or pulse. So it is also called as squaring circuit. As shown in the circuit diagram, the voltage divided with resistor R division 1 and R division 2 is set in the positive feedback. The same values for the divider resistors are used to get the resistance value, that is RPAR, that is RDIV1 divided by RDIV2, that is which is connected in series with the input voltage. So the voltage across R1 is feedback to the non-inverting input. The input voltage V1 triggers or changes the state of output V out every time it exceeds its voltage levels above the certain threshold values. That is called as upper threshold value and the lower threshold value. So let us assume that the inverting input voltage has a slight positive value. So this will cause a negative value in the output. Now this negative voltage is fed back to the non-inverting terminal of the op-amp through the voltage divider. So the value of the negative voltage that is fed back to the positive terminal becomes higher. The value of the negative voltages becomes again higher until the circuit is driven into negative saturation, that is minus V saturation. So now let us assume that the inverting input voltage has a slight negative value. This will cause a positive value in the output. This positive voltage is fed back to the non-inverting terminal of the op-amp through the voltage divider. Thus the value of the positive voltage that is fed back to the positive terminals becomes higher. The value of the positive voltage becomes again higher until the circuit is driven into positive saturation. So this is why the circuit is also named as regenerative comparator circuit. So this is the Smith trigger input and output waveform. Here we can see that the input waveform is a sine wave and we get a square wave in the output. So thank you all for watching this video.